ultimate aim is to put the material to the actual applications, right, where I need some amount of ductility. That is the reason. So the microstructure was the same thing we have summarized here. Finally, which further studies were taken care on the aluminum point to cobalt chromatic nickel molecular. So we need high temperature tensile. Room temperature tensile I did not show here because we got precipitation hardening, we got very extremely high strength, we got it around 200 G2 GPa. I'm not presenting here, but high temperature I'm presenting here. The initial conditions cold rolling and really 1200 degrees for 1 hour. Because I'm doing high temperature, right? I have to first stabilize the microstructure. If you don't stabilize the microstructure, high temperature during tensile testing itself, my microstructure can evolve. So I can't study what is exactly the effective. LI is actually behaving like that is because during the microstructure evolution, the behavior is becoming like that. So first I stabilize the microstructure at 1200 degrees centigrade for 1 hour, and then I get temperature experiments up to 900 degrees centigrade. I did the tensile experiments, and it is strain dates, different strain dates of the initial grain size is this much, and microstructure also done using SFDSD. This is the initial microstructure after annealing. You can see that there is no continuous matrix is there, and the grain size is much higher grain size and more like equiaxial grain size. Then we need the tensile experiments. Then you can see here a particular temperature regime you will see some kind of serrations will sound. You saw some kind of serration means the stress tensor is not going smoothly, but it's going load dropping and like some kind of waviness we saw in the deformation, including deformation, especially in the 400 to 600 temperature. If you see higher magnification, you will see that there is some kind of serrations are there. What can be the reason? Immediately come to mind dynamic strain aging. So dynamic strain aging can be the reason. How much time is there?
2:30 is the time now.
Okay.
You can continue.
10-20 minutes.
You can continue, sir.
So dynamic strain, this can be a dynamic strain aging. But is it really responsible mechanism? Then start looking at the. You can see that serrations also. The serrations are of different categories because the serrations can be A, B, C, E up to D, E will be there. So basically, we found that serrations can be of A plus C type, but not going further in deeper in that. So the function of strain rate is anything like A type serrations become dominant. As a function of temperature increases, my C type serrations have become dominant. Why? We're not going further deeper in that. We publish that. One more one. I'm sorry. Huh?
It is directly connected. It is directly connected.
Directly connected here, but that's the thing. I'm sure that I have those microstructure. It is. But the thing
Maybe it is loading time. Loading. It is taking more loading times.
I think this is loading.
No, it is not. Or else,
Okay, huh? Oh, same problem. Is it okay? It's not just me. Okay. So different mechanisms can be because anything you observe, you have to find out what can be the reason, right? So different mechanisms can be responsible for that. You take a deformation, use plastic deformation. Sometimes during the plastic deformation, some kind of phases can change. Because the phase changes, you can have this serrations can have. Sometimes order dissolved transformation can take place. Sometimes pinning, when pinning happens, suddenly stress will drop. So in pinning also can become a distillation. Sometimes your brittle sigma phases are there, right? When they fracture, that can give some kind of stress drop. So your brittle phase cracking, for example, you non-indentation, whenever this fracture is there, you see some kind of poppings you can see. And it can be solute, solid solute interaction. Solute dissolution interaction. So this is a microstructure. Room temperature 600 degrees centigrade and 800 degrees centigrade. So here and here we did not see serrations. Serration is the load drops we did not see. But where here we saw the serrations. And you can see there is an RT grip and RT grip. What exactly grip means? Take a tensile test. There is a grip with the way of holding the sample, and the tip will be the which is in the gauge portion where deformation takes place. So the grip portion is basically which not having undergo any deformation, and tip portion is where you undergo the deformation. So the same condition, for example, is both exposed to 600 degrees centigrade, but this is not exposed to any plastic deformation. This exposed to some amount of plastic deformation. So I can compare it. Is the deformation actually producing anything else? You can see all these samples. Okay, I'm not seeing any difference in the microstructure between the grip and tip. That means there is no deformation-induced phase transformation taking place, and I'm not seeing any twinning. So there is no twinning-based what's called the mechanism that is responsible for the serrations. Sometimes what happens is seeing the cracks, right? But the cracks are there here also, but you're seeing both things and seeing the cracks. This is a sigma fit. This is a tip. In the grip portion, you're not seeing fracture of this sigma fit. In the grip portion, where the deformation taking place, my sigma fit is fractured perpendicular to the tensile axis. Definitely, is because of cracking one. But this is there in 200 also, room temperature also, where I did not see serrations. So that means even the 600 I am seeing that I can say that is because this is the reason for the serrations. But 200 also I am seeing the significant number of cracks where I did not see serrations. That means this is not actually responsible for the serrations. And there is some amount of phase transmission of the opposite particles are there. Here is not there. That means here we are not seeing serrations. So phase transmission is not reason for serrations. Only one and only mechanism can be a solute dislocation interactions. So for that, what we did a critical state work. And we talk about the strain rate sensitivity. You know what is strain rate sensitivity? Strain rate sensitivity means when you are changing the strain rate, how it is going to affect your stress. In general, what happens is increasing the strain rate, the stress for the deformation also increases. That is called strain rate sensitive, positive strain rate sensitive. But what happens at high room temperature, strain rate sensitive is generally 0.001, 0.002 like that, very low, close to 0. But the moment you are going to high temperature, you see the strain rate sensitivity of 0.2, 0.3, 0.1 like that you will see, depending on what mechanism operates. But you see here, this is the temperature at 600 degrees centigrade, the strain rate is almost 0 or sometimes negative. That means, in increasing the strain rate, my stress is actually decreasing, or either it is not affecting at all. This is called negative strain rate sensitivity, which is one of the signature for dynamic strain aging. Okay, and this is if you don't want to go into this, basically a normal behavior. And also we saw the literature now, because we don't have the TEM that time. We saw the literature. One guy had done tensile experiments on this LI, which is basically cobalt chrome identical LI. This is not exactly our LI, but this is cobalt chrome identical, all these materials. Then he saw some kind of serrations as well. This one. 873 and 1073 saw serrations. Then he made a single crystal, again cobalt chrome identical, in this case he added aluminum. The moment you add aluminium, this is all basically aluminum cobalt chrome identical. But the moment you remove the aluminum, we are not seeing the serrations. When they add the aluminum, because both are 873 Kelvin only, but the moment aluminum is there seeing the serrations, no aluminum is not seeing serrations. That means aluminum is holding the dislocations. So basically, solute dislocation interactions, how it happens at particular velocity or dislocations, whatever the dislocation is going, the solute atoms are going forming an atmosphere below the dislocation line. Because the solute atoms are spinning here, the energy of the dislocation decreases. So the solute atoms will want to go and sit below the dislocation line. The moment solute atoms sit there, the dislocation don't want to go further. Because the moment dislocation will cut off the precipitate, the solute atmosphere, the strength of the dislocation increases. Don't want it. So it holds by dislocation. Basically, we can say that the solute atoms actually holding the dislocation line. But if you increase the strength, it will suddenly this dislocation will come out of it. That means just suddenly drops. Again, the solute atom go and hold the dislocation. Because the diffusivity of the solute, the velocity of the dislocation line and the diffusivity of the solute atmosphere are comparable. The moment the dislocation go and moving velocity, the solute atoms again go and hold the dislocation. So this kind of holding and dealing, happen. That is the reason we are seeing this decreasing stress, decreasing stress like that. That's the reason for your dynamic strain aging. So that's why you can clearly say from here that interaction of aluminum atoms, because molybdenum is there, which is not there here, but molybdenum is there in alloy, but molybdenum diffusion is too low. It cannot go that fast and hold the dislocations. Okay, so from this we can say that the interaction of the aluminum with the dislocation line might be the reason for the dynamic strain aging in the present alloy. The fracture, how it is happening, we can see the fracture actually going through the precipitates, the matrix and precipitate surface and fracture happening. So this is how it happens. Then further what I've done, finally we want to have the creep, because at high temperature we want normal high temperature, we want high temperature creep also, right? What is creep? Creep is basically take the material and apply constant load, right? And we see how the strain is coming down. Basically it's a progressive degradation of the material under constant load. Generally do the experiments at constant load at high temperature. Generally do the same experiment at high temperature. So I want to show, because I'm saying that my material can be good alternative material for a high temperature applications. I should show my material have very good creep properties, right? That's why we did again 100 degrees stabilization structure, and we did both stress experiments and constant load experiments. and the temperature is between 700 to 800 Newton, and initial stress range from different constant stresses Newton from 50 to 300 MPa, and initial grades is 9 micron, and the weight on microstructure by using SCM and PM. I mean, I think I can show them. This is the creep curve. Creep curve means take the sample and load some load, and by measuring the strain continuous as a function of time. How the strain is changing coming as a function of time, that is basically your creep curve. Typical creep curve, how it is will be, basically, I think you saw in BTech undergrad, right? So there is a primary region is there, where the slope is slowly decreases, and then constant slope, and then slope increases. Generally constant load expense, we show this kind of curve. Right? So that means basically here the slope of this curve is nothing but your creep rate. The creep rate is very high, means the material is very less in creep resistance. The creep rate is very low, I can say the material is a very good creep resistance. I want a material with very low creep resistance. So but what happens in a single experiment, initially the creep rate decreases, which is called primary creep region, and we have constant creep rate, which is the minimum creep rate or secondary creep rate, and then creep rate again increases secondary, tertiary creep region. But if you see the creep curves, most of the creep curves don't have primary. Most of the creep curves don't have the primary creep. So finally, what happens? My main understanding is what is the responsible mechanism for creep. That's what I'm looking at. So one of the signatures is most of the curves do not have primary. Right? So we have done load jump. Load jump is also gone. So there is load jump experiment. Like after certain amount of strain, again we did jump. After certain amount of strain, again we did jump. Again, there also we did not see any primary. And we see the microstructure. Microstructure is there are some phases are there at the range boundaries, and the phases are going into the matrix. But both are same. The gauge and grip both are same. That means there is no deformation in these phase transformations, but this transformation happen because the material is exposing to. So what are compared to what are 800 degrees centigrade. Because grip and gauge both are showing the same microstructural features. Where grip is not experiencing the stress, where gauge is experiencing stress, but both are showing the same microstructure. That means no deformation induced or stress induced phase transformation taking place in this material. And no changes in the microstructure between the gauge and grip portion. Then we see, okay, that graph gone. Okay, so now we showed one graph which is missing, is actually showing that the creep rate of this Li is 2 orders of lower than the creep rate of conventional high temperature LIs of this class, which clearly show that these materials have very good creep resistance as compared to the present conventional materials at the temperature. So now we plotted the creep rate, strain rate, that is slope of the creep curve in the steady state region, and then stress. It's higher, but if you don't understand, don't worry. So now this creep rate can be given by this expression. This is called some empirical, the phenomenological expression is there, where epsilon dot is the minimum steady state creep rate, that is the second stage, what is the creep rate is there, and D naught exponential minus 2R is the diffusivity, and A is the microstructure constant, G is the shear modulus, B is the Bernoulli circle. Sigma by G, sigma is the stress and G is the shear modulus, and is called stress exponent. And D by D, D is the Bernoulli rate, D is the grain size, and P is called inverse grain size exponent. And the exponential QA is the diffusion for diffusion. So here 3 parameters are there. Remaining all we are giving NPQ. This is NPQ, N is the stress exponent, P is the inverse grain size exponent, Q is the acceleration energy. Based on these values, we can tell which mechanism, the dislocation climb is controlling, dislocation glide is controlling, or Navarro herring is the controlling, or which I discussed earlier, right? Or a diffusion along the grain bound, which is called Koebel creep is the controlling. Which is the controlling mechanism, I can tell. So here I am saying my N is varying from 3 to 4, 5 almost. So N is equal to 3 is dislocation glide control creep. Just believe me. N is equal to 5 is basically dislocation climb is controlling. That is the slowest process. But my N is changing from 3 to 4.5. So to normalize it, what we have done, we basically now this is activation energy. Activation energy is I can't use it because I have all the eigenvalue limits are there. So I can't use activation energy as a signature for the mechanism to identify the mechanism. But at strain rate, I normalize the diffusivity of the liquid, and it's just I normalize the shear modulus. Then all the data falling into a single line. It's called master curve. When doing the master curve, you can see that these are the literature data. Whereas this is our data. This is basically our data for different temperatures, 700, 750, 800 degrees centigrade. This is our data. This is the literature data. Is there? I can see that our data is 2 orders of magnitude lower than the literature data, which is again on the main levels. So in this, within the comparison to 100 alloys itself, our strain rate creep rates are much lower than the what is presently reported data on creep data on the 100 alloys. But we have another curve where we are comparing with the P91, 92, which is a present using as a materials in the ultra supercritical thermopower plants. Again, this alloy is showing much better creep resistance. But in the 100 alloys also, this is showing much lower creep resistance. I want the curve to be as low as possible. That's why the strain rates are as low as possible. So that way you can get it from there. And then if you see the slope, it is falling the n is equal to 3. And this is a power law breakdown region, but mostly n is equal to 3. So my point is there is a transition of n is equal to 3 region to power law breakdown region. This is exponential relationship. And no significant primary creep. Again, no significant primary is basically one of the signature for primary creep for the blind creep. I'm not going to go deeper in that. And this is the dislocations. This is the dislocations are there, the DEM. I try to get at how the dislocations are arranged in the material after deformation. This after deformation, calculus the sample from the gauge portion, and using DEM, at least the dislocations are spaced equally. If it is a climb, is the slowest process. What happens? Dislocation will come and close and move close to the climb process. Climbing is difficult because glide and climb, right? That is how the deformation takes place, as I showed earlier. So then you see the dislocation networks. We'll see. When the glide is the slowest process, this glidiness is not coming before reaching that. This dislocation is climbing up. So my dislocation will be very widely uniformly spaced. So now we can see that one. The dislocations are very widely uniformly spaced. There is no dislocation forest. These more dislocations are not forming any piles or like dislocations. They're not forming grouping, right? You can see the widely spaced dislocations. So the results is the no significant primary creepy region and no dislocation cell structure and uniform distribution dislocations, suggesting that dislocation glide can be the rate controlling mechanism for this material at this temperature and stress regime. So with this, I want to conclude that dynamic strain aging characteristic IKC serrations are observed in the intermediate temperature regime. This serration did not see below 400 and above 600 also. In this temperature regime only the serrations and solute interaction with dislocations might be the possible mechanism to be established. And changing the failure mode from transcranial to the intercranial base what happens in the high temperature. And creep rate is 2 orders lower in the present LI compared to the cobalt identical which I showed you before. And dislocation glide control mechanism will be the dominant creep mechanism, which is already mentioned. It is, thank you.
I think 1 hour 30 minutes.
1 hour 30 minutes event.
15 minutes. 15 minutes.
15 minutes.
50. 50.
50 minutes, is it? Thank you. 1 hour 30 minutes is really not good.
Sir, serrations are starting from.
Yeah. First, I will take you.
Yes.
Okay. This really started don't want solutions. Actually, solutions are like that. Fitting is repeat, it's very bad. I did not show one curve actually. The one picture you could not see here. Where actually this is the DAC. DAC means I can get 2 dimensions strain. You know that, right?